Okay, so this is number 21 from 7.4. And I'm going to mostly focus on the partial fractions process and not the integration at the end, because I think the partial fractions is the challenge on these problems. So you've got the original, and your first step, of course, is to factor the denominator and then set up the partial fractions, the beginnings. Keep in mind when you have a repeated factor, you need both x and x squared, because those could both be fractions that would add together to give that common denominator. But you don't need a bx plus c on top of that x squared. That's kind of an exception to the general rule about quadratics because it's a repeated factor. Okay, so that's the setup. Then you multiply both sides by the least common denominator by the x squared times x plus 2, and I'll go ahead and just jam that in there. So you multiply that through, and there's some things that cancel there, of course. You get 1x cancels there, everything cancels over here. Both x squared cancels there, and x plus 2 cancels there. So you end up with this as your algebraic expression that you're trying to solve for a, b, and c. So we've got a couple obvious choices here. You can say if x is if x is 0 is what I was trying to write there. If x is 0, plug 0 in and you'll get negative 2 equals, that term drops out, the third term drops out, and you just get b times 2, which implies that b is negative 1. Okay, so that one's not too bad. And we've got one more that isn't too bad. We can say if x is negative 2, then we get 20 minus 8, so that's 12 equals, and negative 2 makes that term drop out and that term drop out, and we get 4 times c. So that implies that c equals 3. And then you sort of seem to run out of obvious choices. There's nothing else that will zero out a couple of terms, or any terms for that matter. The beauty of this equation, though, that we're trying to solve right here, this equation, is that it's not an equation to solve, it's an identity. Like, it's always true for any value of x. So we know that we can just substitute any other value for x, and we should have a true value. So what I'm going to do here is I'm just going to say, what if, and I'm just making this particular number up because it's easy, what if x equals 1? So if x equals 1, let's see, we get 5, 8, 6 equals, and I'm going to make use of the b and the c that I already know. So when I plug in x equals 1, I don't know a, so this becomes 1 times 3, so I'll get 3a. I do know, though, that b is negative 1, and I'm plugging in 1 for x. So negative 1 times 3 is negative 3. And I know that c is 3, and I'm plugging in 1 for x. So that becomes plus 3. That won't always happen. That was just a coincidence of this particular equation, but these cancel. And it turns out that a is 2. And from there, you can set up the integral and do the integration. Like I said, that part's not hard. So you would be integrating, a is 2, so 2 over x, b was negative 1, so minus 1 over x squared, and c was 3. And like I said, those are easy to integrate. Actually, well, yeah, let's go ahead and just do it. Let's finish it off since we're here. So we'd integrate to 2 natural log of x. This 1 over x squared, keep in mind, is the same thing as x to the negative 2, so that's easy integration. So it becomes plus x to the negative 1, and this would become 3 natural log of x plus 2. Don't forget the plus c. It's possible that in the back of the book they will move this 2 up here and move this 3 up here, and then you could combine the 2 natural logs into a single natural log. I haven't looked in the back to see if they do that or not. I'm not so big on whether or not you do that. I feel like we have the answer. It's integrated. We can use the integrated function to do anything we want to do. So that's number 21.